800 feet below the surface, total darkness. The hum of machinery stops, ventilation dies, the submarine starts sinking into the abyss. You have minutes before the hull crushes like a soda can. This isn't a movie. This is what happens when a nuclear submarine loses all power underwater. And the crew's survival depends on systems most people don't even know exist. Chapter 1. The Cascading Failure. When a nuclear submarine loses all power, it's never just one thing that fails, it's everything at once. The reactor scrams. That means it automatically shuts down, usually because of a loss of coolant flow or a detected anomaly. The main turbine generators that produce electricity stop spinning. The propulsion system goes dead. The lights go out. The control surfaces that keep the boat level stop responding. In an instant, you've gone from a highly maneuverable nuclear-powered warship to a 19,000-ton steel tube with no thrust, no steering, and no way to maintain depth. The immediate effect is terrifying. The submarine starts to sink. Without forward motion and without power to the control surfaces, the boat can't fly through the water to maintain depth. Gravity takes over. The descent begins. USS THRESHER learned this the hard way in 1963. The boat experienced a piping failure that caused a reactor scram. Without power, the crew couldn't recover. THRESHER sank past crush depth and imploded, killing all 129 men aboard. That disaster changed everything about how the Navy handles power loss casualties. Modern submarines are designed with this nightmare in mind, but the margin for error is razor thin. Chapter 2. The Battery Backup. Here's what most people don't know. Nuclear submarines carry massive battery banks specifically for this scenario. The moment main power is lost, the batteries automatically kick in. These aren't car batteries. We're talking about industrial lead-acid battery cells, hundreds of them, capable of delivering thousands of amps. They're housed in dedicated compartments below the main deck, and they're one of the heaviest single components on the boat. The batteries feed essential systems only. Emergency lighting comes on, bathing the boat in red. Critical navigation instruments stay powered. Most importantly, the emergency propulsion motor gets electricity. This motor is coupled directly to the reduction gear and can turn the propeller even with the main turbine offline. It doesn't provide much thrust, maybe 3 to 5 knots maximum, but that's enough. Enough to maintain some depth control, enough to keep the boat from becoming a falling brick. An Ohio-class submarine can run on battery power for several hours if the crew is disciplined about power management. Non-essential systems get shut down immediately. Lighting is reduced to minimum safe levels. Heating and air conditioning stop. Every amp of battery power is conserved for propulsion and life support. But batteries don't last forever. The clock is ticking from the moment main power is lost. Chapter 3. The Depth Control Battle. Without propulsion, a submarine can't rely on forward motion and control surfaces to maintain depth. The crew has to fight with buoyancy alone. The control party immediately checks the depth gauge and rate of descent. If the boat is sinking, they have seconds to react. The first move is to verify trim and check all ballast tank status. Are any tanks flooding that shouldn't be? Is there a weight imbalance? If the descent continues, the next step is emergency ballast tank adjustments. The crew can blow specific tanks using high-pressure air to add buoyancy in precise locations. This is a delicate operation. Blow too much and the boat rockets toward the surface uncontrollably. Blow too little and you're still sinking toward crush depth. The diving officer is making calculations in real time. Depth, rate of descent, remaining high-pressure air, battery power available, time until the reactor can be restarted. Every variable matters. If standard measures aren't working and the boat is still descending toward dangerous depths, there's one last option. The emergency main ballast tank blow. Chapter 4. The Chicken Switches. In the control room, there are mechanical levers that submariners call chicken switches. These are the emergency blow activators, and they're designed to work without electrical power. When you throw these switches, you're opening valves that dump 4,500 psi air directly into the main ballast tanks. This bypasses all normal controls and piping. It's a brute force method of adding massive positive buoyancy in seconds. The effect is violent. The submarine rapidly lightens and the bow pitches up, sometimes to extreme angles. The ascent rate can hit tens of knots. In the final stages near the surface, the boat is essentially rocketing upward. This is not a controlled maneuver. This is a last resort emergency procedure used when the alternative is uncontrolled descent toward crush depth. The rapid pressure change puts enormous stress on the hull, equipment can break loose, crew members can be injured, the boat can broach the surface, meaning it comes up so fast it partially leaves the water before crashing back down. But it works. The emergency blow system is mechanically simple and doesn't require ship's power. It's the ultimate backup, the system that can save the boat even when everything else has failed. The problem is what happens if flooding is the root cause of the power loss. If water is pouring into the boat faster than you can pump it out, adding buoyancy might not be enough. The weight of the water could overcome the positive buoyancy from the blow. In that scenario, you're in a race between the flooding and your ability to surface. Chapter 5. The Atmosphere Crisis. Let's say the crew stabilizes the boat at depth using battery power and emergency procedures. The immediate crisis is over. But now they're facing a different problem: the atmosphere. Loss of main power knocks out normal ventilation and air conditioning. The fans stop. Air stops circulating. Heat and humidity start building immediately. A submarine generates an enormous amount of heat. The reactor is still producing decay heat even after shutdown. Electronic equipment is running. Most significantly, 160 human bodies are producing metabolic heat and exhaling CO2. Studies simulating power-off scenarios show that internal temperatures can climb rapidly. Without ventilation, hotspots develop near equipment. Humidity spikes. Within hours, the environment becomes oppressive. Crew members start sweating heavily, which leads to dehydration. Cognitive performance degrades, decision-making suffers. This is exactly when you need people thinking clearly, and the environment is working against them. The atmosphere regeneration systems continue to operate on battery power, but they're highly exothermic. The CO2 scrubbers generate significant heat as they work. The oxygen generation system, if it's running, also produces heat. Procedures call for switching to lower heat backup options where available and minimizing crew activity to reduce metabolic heat and CO2 production. The crew breaks out emergency breathing devices if CO2 levels climb too high. They ration physical activity. They drink water constantly to stay hydrated. And they wait while the engineering team works to restore main power. Chapter 6. The Reactor. Restart. The engineering team is fighting to bring the reactor back online. This is the only real solution. Batteries are temporary. Emergency systems are stopgaps. The boat needs its reactor. Modern procedures allow for faster reactor recovery after a scram than older protocols did. The lessons from THRESHER were brutal but clear. You need to be able to restart quickly in an emergency. If the scram was caused by a transient issue, a momentary loss of coolant flow, or a sensor glitch, the reactor can potentially be restarted within minutes. The reactor operator follows emergency procedures to verify that conditions are safe, that coolant flow can be restored, and that control rods can be withdrawn. If there's residual steam in the secondary loop, the turbines might still be turning slowly. That residual energy can be used to generate some electricity, buying time and reducing the load on the batteries. But if the scram was caused by a real casualty, a pipe rupture or equipment failure, the restart becomes complicated. The engineering team has to isolate the problem, verify that the reactor plant is safe, and potentially work around damaged systems. This takes time. Time the boat might not have. The entire crew is aware of what's happening. They can feel the boat's attitude in the water. They can hear the reduced noise level without main systems running. They know the engineers are fighting to save them. And they know that if the reactor can't be restarted, the options get very limited very quickly. Chapter 7. The Disabled Submarine Scenario. If the boat stabilizes at depth but can't restore main power, it becomes a disub, a disabled submarine. This shifts the situation from immediate crisis to medium-term survival and rescue. The command team assesses the situation: hull integrity, remaining battery capacity, high-pressure air reserves, atmosphere status, internal temperature, external depth and seabed conditions, communications capability. If the boat can reach periscope depth or surface, it can call for help. Modern submarines have multiple communication systems, including emergency buoys that can be released to float to the surface and transmit distress signals even if the boat is stuck on the bottom. The message goes out: submiss, submarine missing, or subsunk, submarine sunk. This triggers a massive response. The Navy maintains dedicated submarine rescue systems specifically for this scenario. Deep submergence rescue vehicles that can mate with a submarine's escape hatches and extract crew members. But rescue takes time. The response can take anywhere from 3 to 7 days depending on location. That means the crew has to survive on board until help arrives. Survival procedures are strict. Minimize activity to reduce heat and CO2 production. Ration food and water. Maintain atmosphere control using emergency systems. Keep crew morale up. Wait. The psychological pressure is immense. You're trapped in a steel tube on the ocean floor. The air is getting worse. The temperature is climbing. You can't leave. You can't fix the problem. All you can do is wait and hope rescue arrives before your life support runs out. Chapter 8. The escape option. If rescue isn't possible or won't arrive in time, there's one final option: individual escape. Modern submarines have escape trunks, small chambers that can be flooded and pressurized to allow crew members to exit the boat and ascend to the surface. Each sailor wears a submarine escape immersion equipment suit, essentially a survival suit with a built-in hood that provides breathable air during ascent. The procedure is dangerous. You're essentially doing a free ascent from depth, which carries serious risks: decompression sickness, pulmonary barotrauma from expanding air in the lungs, nitrogen narcosis if you're deep enough, hypothermia once you reach the surface. The maximum depth for escape is around 600 feet, and that's pushing it. Deeper than that, and the risks become prohibitive. Even at shallower depths, if the crew is heat-stressed, dehydrated, or suffering from CO2 buildup, their chances of surviving the ascent and the time in the water afterward drop significantly. Escape is a last resort. It's chosen only when staying aboard means certain death and rescue is impossible. It's a calculated gamble that some will survive rather than everyone dying together. The decision to abandon ship is the hardest call a submarine captain will ever make. Chapter 9. The THRESHER Legacy. USS Thresher's loss fundamentally changed submarine safety. The Navy implemented the SubSafe program, a rigorous certification process that covers every system critical to maintaining hull integrity and recovering from casualties. Piping systems were redesigned, welds were improved, quality control became obsessive, emergency blow systems were simplified and made more reliable, procedures for reactor scrams were rewritten to allow faster recovery. The changes worked. Since SubSafe was implemented, no certified US submarine has been lost due to hull failure or inability to recover from a casualty. The program has prevented disasters that would have killed thousands of sailors over the decades. But the threat remains. A submarine operating underwater is always one major casualty away from disaster. The systems are robust, the training is intense, and the procedures are proven. But the ocean is unforgiving and equipment can fail, and every submariner knows the risks. They know what happened to Thresher, they know what can happen if everything goes wrong, and they volunteer anyway, trusting in their training, their equipment, and their shipmates. Chapter 10. The reality. So what really happens when a nuclear submarine loses all power underwater? It's a time-critical emergency that can escalate from controllable to catastrophic in minutes. The crew fights to maintain depth using battery power and emergency propulsion. They manage buoyancy with ballast tank adjustments. If necessary, they execute an emergency blow to force the boat to the surface. They work frantically to restart the reactor and restore main power. If they succeed, the boat recovers and continues its mission. If they can't restore power but stabilize the situation, they become a disabled submarine, waiting for rescue. If they can't stabilize and can't surface, they face the choice between staying aboard and attempting escape. The systems exist to handle this scenario: the emergency propulsion motor, the massive battery banks, the emergency blow system that works without electrical power, the procedures that allow rapid reactor restart, the rescue system standing by. But ultimately, survival depends on the crew, their training, their discipline, their ability to execute emergency procedures under extreme pressure, their willingness to fight for every second, every foot of depth, every amp of battery power. Most submariners will serve entire careers without facing a total power loss. But they train for it constantly. They drill the procedures until they're automatic. They maintain the systems obsessively, because they know that if it happens, there's no margin for error. The ocean doesn't care about your training or your technology. It will crush your submarine if you give it the chance. The only thing standing between a crew and disaster is their ability to execute when everything goes wrong. That's the reality of submarine service. That's what these sailors face every time they dive. And that's why losing all power underwater is the nightmare scenario that every submariner hopes never happens but is always prepared to fight. We are committed to releasing 3 videos a week. Like, share, subscribe, and hit the bell icon for more Anchor Watch.